Welcome back. In this short video, we're going to do a comparison of the work associated with reversible processes to those of irreversible processes and see why the reversible processes are very important in thermodynamics. Okay, so let's look at the case of the compression or expansion of a gas. In this case, we're going to look at that compression expansion when it's done reversibly. So imagine you have some piston cylinder apparatus, and here's my cutaway view here. And when the gas is at equilibrium, then it will be exerting a force on the piston that's equal to the external force here. So this whole system will be at equilibrium with the surroundings when the force of the gas is equal to the external force acting on the piston here. So now we have a system where inside the pressure is identical everywhere inside this gas, and so the pressure just behind the piston, the pressure that's responsible for the force that's pushing on the piston, is identical to all the pressure everywhere else in this gas at equilibrium. So at an equilibrium state, then, the external pressure, which is equal to the pressure behind the piston, is also equal to the equilibrium pressure of the gas here. So let's just be clear about all these different pressures here. The equilibrium pressure of the gas, the pressure just behind the piston, and the external pressure that's being applied to the piston. Now, when I do a reversible expansion and I reduce the pressure out here and let the gas expand, then I get work out of this system, and I follow this process reversibly along a path where I go from 1 and I expand out in my volume and the pressure is going down, and the area under this line is the negative of the work that I get out of the system. And because the system is at equilibrium all on the way, then this line is well defined by the equation of state for the system, because the equation of state describes the equilibrium state. So at every point I'm in equilibrium, and the equation of state predicts what the relationship between the pressure and the volume will be. Similarly, when I'm doing compression and I'm increasing the force here and I'm compressing the gas, if I do this reversibly so slowly that I'm always at equilibrium inside here, then again I have this condition here, and I come back when I'm compressing from 5 liters back to 1 liters along exactly the same path, which is the path described by the equation of state for the gas at equilibrium. All right? And the bottom line then is that the area under this curve, of course, is the same whether you're expanding or you're contracting. In one case, you're getting work out of the system. In the other case, you're doing work on the system. So in one case, the work is negative because the system is losing energy for expansion. And then in the other case, the work is positive because you're compressing the gas and you're putting energy into it. But in either case, the absolute value of the work that you get from compression and the work that you get associated with expansion are equal to each other than the opposite sign here. So in this case, you see that for reversible processes, the area under the curve is the same, and the expansion and compression work are identical but just opposite in sign. Okay, so the work that you put in, you can get exactly the same amount of work out. Now, let's consider what happens when you do irreversible compression. Now, in that same piston cylinder apparatus, if I start pushing this piston in, but I don't do it slow enough that I remain at equilibrium over here, then what I expect to happen is that immediately after I start pushing, there's going to be a higher density of gas immediately behind the piston than there is over here further away from the piston. So what I end up having is a pressure gradient inside my piston cylinder apparatus. So this is no longer at equilibrium. I'd have to wait a while, and eventually, as I said before, at the speed of sound, this would eventually equilibrate and you would get a uniform pressure inside here. But in the instant that I push, there is a higher density of gas here than there is over here, and if I continue pushing quickly, then I'll never reach equilibrium before I go to the next state of higher density behind the piston. So in this case, the pressure behind the piston is always going to be higher than the pressure over here. It's always going to be higher than the equilibrium pressure would have been. If I waited for it to come to equilibrium, then the whole thing would be at a lower pressure than what I have when I initially push it in. So the pressure felt on this side of the piston is higher than the equilibrium pressure. So that means that if I'm doing a compression from, say, 5 liters down to 1 liters, from the external pressure, if I plot the external pressure versus volume, the external pressure is always going to be higher than the reversible compression curve. Remember, the reversible compression is the equilibrium pressure, and that's always going to be lower than the pressure that's immediately behind us if I push it in too quickly. So that means the path, the external pressure path, is going to be above this line for the reversible compression, and it's going to stay above it pretty much till we get to the end, and then we reach the end and we're at equilibrium with new state. But now what you see is that the path integral, which is, it takes us to the area underneath this curve, tells us that the area is greater than the reversible, the irreversible area is greater than the reversible area. So we had to do more work irreversibly compressing the gas than we would have done if we had done it reversibly. So it takes more external force to compress the gas irreversibly than reversibly, and you can see that that's because the pressure behind the piston as we do this irreversibly is always going to be higher than what the equilibrium pressure would have been, and so the area under this curve is always greater, and so we have to do more work. All right, so we did more work in the compression than we would have done if we had irreversibly than if we had done it reversibly. What about expansion? Well, if you let it expand from, say, 1 liter out to 5 liters, if you let it expand irreversibly, then what happens is as soon as you let this piston reduce the pressure and the piston comes out, you're going to have a lower density immediately behind the piston than you have in the other regions of the piston. So again, you're not at equilibrium. So this part of the system, just immediately behind the piston associated with PB, is going to be a lower pressure than the equilibrium pressure would have been, and it's going to be higher over here. So what's felt by the other side of the piston, P external, is going to be a lower pressure than the equilibrium pressure. So if I expand, and I start out at 1 and I expand irreversibly, then the pressure, the external pressure, which is feeling this PB, is going to be lower than what would have been the equilibrium pressure as we expand. But eventually we get out to 5 liters and we reach equilibrium, but along the way the area under this is less than it would have been if we had expanded it reversibly. So now you see that we extracted, we got work out of the system in expansion, but since we did it irreversibly, we got less work than we would have gotten if we had done the expansion reversibly. So what we see is less work is recovered reversibly expanding than irreversibly expanding than reversibly. So the bottom line is that the irreversible compression work is going to be more than the irreversible expansion work. So it's going to take more work to compress, and you're going to get less work out expanding if you do it irreversibly. And when you do it reversibly, the work you put into compression, you're going to get back out reversibly in the expansion step. So what happens then is that the energy that could have been transferred as work, thermodynamic work, now gets dissipated into the energy of the system and is not available for doing work. So that's it for this short video. In next video, we're going to step into the first law of thermodynamics.